Yeah, if you look at news sites that present news about artificial intelligence, it's usually machine learning techniques. And you might ask why still use symbolic techniques. And if you ask researchers in that area, they will usually tell you, well, we are explainable. If you get a result, you can be quite sure that it's correct. If you use your roots and yeah, you can verify that the roots are correct, like if it has two pairs of polar sides, it's a parallelogram. Other roots tell you it's a kite, and if it's both a kite and a parallelogram, then it must be a rhombus. And yeah, we inspect all the roots and we see the roots make sense in some way. Maybe we need a textbook, but then we can be sure that our result is correct. This is the theory. In practice, we don't really do this by hand. We really individually select a rule and apply it, but we have our database of elements that we want to classify. We define our rules, and we all give it into an engine. And this engine spits out some results. And it's optimized to work with large millions or even more number of facts, and does not do the simple pen and paper version, but many optimizations. And despite now we are not really sure anymore whether the result that we get is actually correct. And we had a theorem proving conference, so you might say, well, just verify the engine. And my co-authors thought it might be a bit too large for a master thesis. And what can be done instead? And many of these engines can do more than just spit out results. They can also tell you why this was true by giving you a certificate. And instead of verifying the engine, we will build a verifier that takes results and certificates and tells you whether they match or not. And verification is a bit simpler than computation usually, so this is possible to do in a formally verified way and still fit in the time limits. And in what cases will we do that? So we use Datalog and we verify it with Lean. Nonetheless, it's not required for the talk to have an understanding in either of them. We will introduce what is needed about Datalog and don't really use specifics of Lean. And this is joint work with Lukas Gerlach, who's also in the audience, and Stephan, Mennicke, and Markus Krötzsch. So what is Datalog? So we have a database on the top left, and it's a collection of atoms. So like in first order logic, but we have no function symbols, so only constants, and also no variables here. And these atoms have an edge relation, so they naturally are a graph. This is the database, and we have a program that tells us what are we interested in. And the program is then on the bottom left. It's a set of rules, 2 rules. Each rule has a body and a head. The body can have multiple atoms. Can I use this? Yeah. So this is the body of the first rule. The arrow points to the head. And the second rule has 2 atoms in the body. And in this case, these atoms can contain variables recognizable by the question mark in front of it. And how do you interpret these? Well, the body atoms are all combined with an and the arrow is just an implication written in the other way. in logic programming, and all rules are universally quantified by all variables. So it's just a fragment of first-order logic, so we can try to find models for these, but maybe not all models are useful. So you see there's no negation, so we could start by making every possible atom true in our result and have a model, but this is not really desirable. We somehow only want what's actually needed. And this is called a minimal model. So in this case here, the minimal model of T is this blue arrow, blue graph. So it contains all edges, and in general, we have the transitive closure by this program. So we have elements that are already connected, and if there's another edge, well, we add it to the transitive closure. And this is the minimal set of atoms that we need, the least model, and this is usually done by intersecting over all models. And at this time, when we formalized this, we had to make a slight detour, and it was not that easy to do this in Lean, but we can make an equivalent logical statement that has the same effect. And all the other syntax and semantics could be pretty much formalized from the textbook without many adaptations. Okay, so in order to do the semantics, we could now just find all models, intersect them, but this is maybe not the best way to do this. So how do the engines do this? So we start with our model. It has all our database elements, and we have the program. And now we can take a rule, the first rule, and we apply a function, a grounding that maps every variable to some constant, and now have a rule whose body is satisfied as it occurs in the current model, but the head is not there. So in order to make this true, we add the head. And we mark this as some kind of graph. And then there's another rule. Now we have of the second kind, which is also there is the body true, but not the head. So again, we add the head. And this forms a proof tree. And these proof trees are what engines give us, and these are our certificates that we want to check. And we can formally prove that all atoms that have a valid proof tree for a given database and program are, so the proof theoretic semantics are equal to our model theoretic semantics. So this formal proof tells us that we probably did formalize both of them correctly, or we made an error in both. But in some sense, it increases our confidence that our formalization is correct. Okay, now we have our certificates. How do we check them? So the trees in Lean can be defined nicely inductively. We have the same tree, and we use the induction. We just go from top to bottom until we reach leaves. The arrows are written in the way of the program. So at the top, this is not a leaf, it has children. And then it must be the result of a rule application. So we have to check, is there a rule that matches the current node as its head and all its children in the body? And this uses techniques that were used by Ben-Zaken et al. In a COG-based Datalog formalization. Afterwards, they go in a bit of a different direction than us. But now we use partial functions that are called substitutions. And yeah, this requires us to not specify for every element what is supposed to map. So the x is mapped to 1, z to 3, and y is currently unmapped. And using this, we can write a match procedure that goes along our structure and takes a look if it's possible. And we show that this for a given rule and ground rule, so the ground rule has no variables, is true if and only if there's a substitution. This is the program verification. And we additionally show that substitutions or groundings don't matter for this when we get from a normal rule to a ground rule. Because the groundings are easier to work with, but not so good to verify. And now we would go to the next one and ask for the leaf, and there we have to check if it's from the database or not. And this was not that much the focus of our work, so we have the infrastructure ready for this, but we mainly work with a database that accepts everything because yeah, we would need to build a lot of infrastructure to actually check if this is correctly in the database and build some kind of data management system in Lean with it. It's a bit out of scope. So if you use it, you have to check yourself if the leaves are in what you've in the files that you have given. And other than this, we can now fully verify trees. You just have to remember this. So trees are like the textbook way of doing this, but maybe not optimal. So in here we have added another rule in red, but the U just hides T. It's just an alias. And now we have here twice T and U's, but essentially just twice T. This leads to duplication in proof trees. Here, it's not that difficult because the slide is not large enough, but in a larger example, this leads to exponentially large proof trees and makes it not the ideal certificate that we want. So instead, we define proof graphs by merging vertices that have the same label and want to use this in our as our new certificates. And these cannot be defined that easily inductively. So the next steps are we need a practical graph model to work with and implement and verify depth first search in Lean to check the inference like we did for trees, and also this graph needs to be acyclic so that an element does not justify itself. We start with a graph model, and you may ask, well, why do so much work? Just use what Mathlib does. And at least at the time that we wrote it, there was only undirected graphs on Mathlib. And in this kind of graph, you don't really see, is U used to derive T or is T used to derive U? So we really need something directed, and also the adjacency matrix formulation is not that ideal for algorithms. So we defined our own model. We started like this. We wrote a structure. It has a list of vertices, some function that maps a vertex to its predecessors, and yeah, we want this to be complete, that we don't somehow get out of the graph. And with this, we can use this quite easily in proofs and also to write the depth first search. We have this explicit list of vertices here instead of like the mathlib approach uses the whole type as the vertices because this was easier for parsing. So this is easy to use. And if we, when we started to actually evaluate it in practice, it turned out to be not that great. And trees were still better than graphs, despite our theoretical thinking. So we need something a bit faster. And for this, we went to hash maps. So we defined a pre-graph as a hash map. Its keys are the vertices of the graph, and each key maps to its predecessors. And we have, again, the completeness predicate. And a graph is then just a complete pre-graph. And now we actually were fast. And we're beating trees. It has a bit of a negative part, which is not that true now. But at this time, the hash map was not that well verified. So the FRO and also we added a bunch of lemmas for hash maps. So if you use it now, you should probably not longer have this negative point anymore. Okay, we have a graph. Now we can implement depth first search on it. And yeah, we have, again, it's pretty standard. We have some kind of large loop that codes it on every vertex, and then an exploration function that goes along each connected component. And it's easy to see what we want for the large loop. Well, it checks if some kind of function holds for every vertex and that there's no cycle. It's not that easy to see what do we want for this step exploration function. And well, the other thing, the cycles are a bit of a global criteria and not depend so well on a single vertex. And you might want to start, well, you say, if it's in a cycle, then it definitely should throw an error. So if we call it on C, we go to B, go to A, go to C, it sees it's in a cycle, it should call an error. The problem is D is not in a cycle, but would reach C and still result in the same error, so we can't prove it here. We need something that propagates back, so we use the reachability from a cycle instead, and this holds for also for D, and using this and many inductions that mainly care about how to combine and the results of different branches, we have now a fully verified implementation of depth first search in Lean for our graph model. For completeness, there's also a third way of proof that we accept. We call them ordered proof graphs. It's again a graph, but not given as a list of edges, which requires us to make sure that there's no cycles, but it's a list of edges where every edge tells us, or every result, sorry, tells us why it was derived. And this can only refer to earlier indices. So if you have seen proofs that such solvers give for if they can't find a model, it's the same structure. And using techniques as similar for the trees, also this can be correctly verified. Okay, we have now three ways to accept graphs or proofs as graphs, as two kinds of graphs and as trees. And I've talked a bit about speed, so let's evaluate this. How do we do this? We took an engine, a Datalog engine called Nemo, that is also developed in Dresden, and used different scenarios and asked for asked for certain elements and their derivations and gave them to our lean tool. At first, we did not manage to find any case where the tool tells us that there's something wrong, so maybe they are quite capable developers of Nemo. And what do we want to achieve? Well, we want to compare it with the Nemo time. If we take much longer than Nemo to verify, the user probably wouldn't do it. And this is the case. So we have four scenarios. The second is not displayed here. It's the example with exponential proof trees. There the tree model drafts everything. And if you compare it, well, we are usually not that much slower, or in many cases even faster than the resulting computation. So I think it's in general doable to do this. It depends a bit on the scenario which is best. So in the first scenario, we have a long chain. There's not much reuse. All models perform quite similar. In the 1B scenario, we ask for all facts to be verified of a long chain. There's a lot of reuse, but trees don't have this reuse. They have to check this again and again, so the trees performed quite badly. And the third one was a real-world medical ontology, and the ordered proof graphs are maybe the fastest in most scenarios, but require more work to get the certificate because this does not match what Datalog engines typically output. And this is not limited to Nemo. You can use any Datalog engine you want. You just have to write a short script that transforms this into a JSON-based output and then use our lean tool. Okay, why still look into the paper? If you want to know a bit more how we have proved things, a bit more of our implementation decisions, you can look in the paper. And also you will see what we have seen so far is only soundness. So a Datalog engine that never outputs anything would be perfect in this criteria we have seen so far. So we have started to build a prototype for verifying the completeness. The problem is this quickly runs into the case that you actually build a Datalog engine in Lean, and then you are either not verified or not fast. And we are currently not fast. What are further open questions, except making this more fast? Now you have to use these somehow independently of the engine. Can we integrate it in a way to make it simpler for the user, but still keep the guarantee that it's correct? And also, our kind of Datalog is quite textbook-like. So we have, for example, no negation, which is commonly available in many engines. But this requires somehow proving that an element is not there, which again looks a bit like completeness. So it's not really obvious how to check the proofs efficiently there. In any case, if you ever come in a scenario where you are unsure if the Datalog result you get is correct, you know what you can do. And thank you for the attention.